Assalamualaikum warahmatullahi wabarakatuh, and a very good day everyone. Today I will be presenting on my research project entitled Design of Multi-Wavelength EDF-Raman Lasers Utilizing Mach-Zehnder Interferometer. I'm Nani Fazlina Naim from School of Electrical Engineering, UiTM, Malaysia. So basically this presentation is for Photonics Meeting 2021 conference. As an introduction, so we know that multi-wavelength fiber laser has many potential applications such as in instrumentation, testing, sensing, temperature sensors, optical fiber sensors, wavelength division, multiplexing communication, and many others. Multi-wavelength fiber laser can be designed with varieties of cavity structure such as linear and ring cavity. For linear cavity structure, it can be divided into two, which is either unidirectional or bidirectional cavity. In order to produce multi-wavelength, an interferometer is required within the laser cavity. So basically, this interferometer technique employs superposition of electromagnetic waves. Major issues in producing multi-wavelength for erbium doped fiber is that the erbium ion saturates most homogeneously at room temperature. Thus, it prevents stable multi-wavelength. So basically for EDF, the issues is that it has unstable multi-wavelength. Okay? But for Raman amplification, it has improved in noise figure and also gain flatness. So this is the improvement of Raman amplification. However, this Raman amplification, it has spontaneous Raman scattering which will produce disturbance to the amplified signal. So that is why in this project, we will combine the EDF and also the Raman amplification to design a better multi-wavelength laser. So the objective of this project is first, to design a multi-wavelength fiber laser in unidirectional, bidirectional, and ring cavity structure. The second objective is to simulate a multi-wavelength fiber laser with optimum number of lacing lines, peak power, side mode separation ratio, and wavelength spacing. And the third objective is to determine the most optimized design of multi-wavelength fiber laser. The methodology of this project is as follows. So as I have mentioned before, there are three types of structure for this multi-wavelength laser. The first one is unidirectional linear. So let's take a look at this unidirectional linear. So we can see that it is just a linear structure. Okay, we have the optical source here, which is the laser diode at 1480 nanometer. We have the pump power at 1450 nanometer and 1460 nanometer. Okay, so the EDF and also the Raman amplifier is actually the amplification process. And then the signal will pass through the Mach-Zehnder interferometer, the IIR filter to filter all the unwanted signals, and finally the gain flattening filter. Okay, so of course the function of this GFF is for gain flatness. And finally the signal, okay, the multi-wavelength laser will be observed using optical spectrum analyzer. Okay, so let's look at the second structure, which is the bidirectional linear. Okay, so we can see here we have circulator. Okay, we have circulator 1 and circulator 2. Okay, and the rest of the devices are just almost the same, okay, as the unidirectional structure. Okay, the circulator, the function of the circulator is basically to get a bidirectional signal, okay, so that the bidirectional structure is produced. Okay, so let's say we have a signal that pass through this circulator, and then the circulator will reflect back, okay, to reduce the loss. And finally, okay, this multi-wavelength laser will be observed using an OSA at this part, okay, at this optical spectrum analyzer. Okay, the function of other of these components are just the same, just like what I have mentioned before. Okay, so let's look at the third structure, which is ring cavity structure. Okay, so here we can see that the shape is in ring structure. So that's why we call it as ring cavity structure. Okay, so this is our laser source, pump power. We have the amplification from EDF and also the Raman amplifier. We have the polarization controller to control the polarity of the signal. We have Mach-Zehnder interferometer, filter, GFF, and finally, the spectrum or the multi-wavelength laser will be observed using optical spectrum analyzer. Okay, so let's look at the result and discussion part. Okay, so let's determine the most optimum EDF length. Okay, so this is actually the result of power versus wavelength for erbium doped fiber amplifier gain with different EDF length. Okay, so this is the EDF length. Okay, so we can see the higher the EDF length, the higher the power. Okay, so the higher the power, the better the design is. Okay, and actually at this point, the gain has already saturated. Okay, so basically for this structure, the most optimum EDF length is actually at 10 meter. Okay, so we can see 10 meter is blue line here. So it has the highest power. Okay, so for unidirectional linear cavity structure, the most optimum EDF length is at 10 meter. Okay, so this is the result for bidirectional linear cavity structure and also for ring cavity structure. Okay, so from here, we can also see that the most optimum EDF length is at 10 meter for bidirectional linear and also for ring cavity structure. Okay, so we can conclude here the most optimum length for EDF is at 10 meter. Okay, so let's look at the most optimum Raman amplifier length. Okay, so for Raman amplifier length, we also have the graph of power versus the wavelength. Okay, so this is actually the power or the gain, which is in dBm. Okay, so from here, we know that the higher is better. Okay, and this is the Raman amplifier length. Okay, the higher the length, okay, the higher the power. Okay, but at certain point, it will saturates or it will be a constant. Okay, and for this structure, the best or the most optimum Raman amplifier length is at 12 kilometer. Okay, so we can see at 12 kilometer, it has the highest gain. Okay, so at 12 kilometer is the most optimum Raman amplifier length. Okay, so the same values actually happen for bidirectional linear cavity structure and also ring cavity structure. Okay, so the most optimum Raman amplifier length is at 12 kilometer. Okay, so for both bidirectional and also ring cavity structure. Okay, so number of lacing lines with different pump power. Okay, so number of lacing lines, we have calculated it based on the threshold power. The threshold power that we have decided is at negative 70 dBm. Okay, so from here we can actually calculate number of lacing lines. Okay, so these are number of the lacing lines. Okay, so the higher the number of lacing lines, the better the design is. Okay, so this is the number of lacing lines versus the pump power. Okay, this is for unidirectional, bidirectional, and also ring cavity structure. Okay, so we can see here, the higher the pump power, the higher the number of lacing lines. Okay, so at certain point, it will saturate or it will become stable. Okay, so the most optimum pump power for this case, we have chosen it to be 1000 milliwatt of pump power. Yeah? So from here, we can get the number of lacing lines. So basically, the highest number of lacing lines for this structure is for ring cavity structure. Whereas for ring cavity structure, it has 19 lacing lines at 1000 milliwatt. Okay. Okay, so let's look at peak power with different pump power. Okay, so this is the peak power. Okay, the peak power versus the pump power. Okay, the peak power of the lacing lines actually. Okay, so this is for unidirectional, bidirectional, and also the ring cavity structure. Okay, so basically if we can see here, the highest peak power is actually obtained by the bidirectional linear cavity structure. Okay, but if we look at the spectrum, even though we have the highest peak power for bidirectional, the spectrum is unstable. Okay, the most stable one is actually for ring cavity structure. Okay. Okay, so this is actually the summary for all the results. Okay, we have three structures: unidirectional, bidirectional, and ring cavity structure. Okay, so for unidirectional, we have the highest number of lacing lines of 18, okay, with peak power of negative 17.9 dBm and average SMSR of 49.2 dB. Okay, for bidirectional linear, the highest number of lacing lines is 17 with highest peak power of 1.6 dBm and also the average SMSR of 30.3 dB. Okay, and for ring cavity structure, okay, it has the highest number of lacing lines, which is 19. Okay, the peak power of negative 19 dBm and the average SMSR of 49.5 dB. Okay, so in conclusion, multi-wavelength EDF-Raman fiber laser utilizing Mach-Zehnder interferometer has been successfully simulated using OptiSystem software. Okay, the most optimum gain is obtained when EDF length is at 10 meter and Raman amplifier length is at 12 kilometer. Okay, the best configuration is ring cavity structure, which produce 19 lacing lines with 49.5 dB of SMSR and negative 19 dBm of peak power. So I think I would like to stop now. Thank you everyone and Assalamualaikum warahmatullahi wabarakatuh.